Hello students, welcome to another video of metric space. So we will start the second chapter. The chapter second is completeness. Second chapter, completeness. So in this chapter, first of all, you will see the definition of sequence in metric space. Definition of sequence in metric space. Sequence in metric space. A sequence in metric space is just a function from set of natural numbers to some metric space xd. So the definition is sequence in metric space xd is a function suppose small x from function x from set of natural numbers to a metric space x. Sequence in metric space is just a function from a set of natural numbers to some metric space xd, and it is denoted by xn or sequence xn. It is denoted by directly xn or in open bracket xn. Now second definition is subsequence. Definition of subsequence. These definitions you have already seen in the real analysis, but in that real analysis sequence is just function from natural numbers to real number. Now here the sequence in metric space is just a function from natural numbers to some another metric space, natural numbers to metric space. So in next definition is subsequence of a sequence, subsequence of given sequence. Now as we know that set subset, that is the subset of any set is just the elements from that set which are less than or equals to given superset. Similarly in the subsequence just a restriction to this function from some set subset of natural numbers to x. A subsequence in a metric space, a subsequence in a metric space is the restriction of function x to an infinite subset, to an infinite subset. That is the restriction of x over set of natural numbers from some set s to x, This we have this s as a subset of natural numbers for that, and this s for s n1 is less than n2 is less than so on nk is again less than all the elements. For yes we have, then we have subsequence. Notation of the subsequence is xnk of a sequence xn. We have subsequence xnk of a sequence xn where this nk is greater equal some k. Here this nk greater equal k for all k belongs to set of natural numbers, for some k belongs to natural numbers. So first of all, sequence in metric space. Sequence means in general the sequence means just a definite order of some elements. Sequence is nothing but if we arrange the elements of any set in some definite order or according to some definite rule, then we call that as a sequence. So here clearly sequence is in metric space is just a function. Function means a rule that assigns every element of this domain to some element of codomain. Here domain is set of natural numbers, codomain is some metric space. So function x from set of natural numbers to some metric space x means sequence means some definite rule. X is a definite rule which arranges every element of natural number to some element in metric space. So, sequence is nothing but a rule that assigns, that arranges every element of domain to some another element in codomain. Now, subsequence means in general, in casual ways we can say that subsequence is just a subset of this set of elements, that is set of this sequence. So, subsequent proper definition of subsequence means just if we restrict this function from set of natural numbers to x, and restriction of this function means suppose S is a subset of these natural numbers, S is subset of natural numbers, infinite subset of natural numbers, then function from this set S to x, this S is subset of natural number and function from S to x is just a subsequence. Now, we will see the next definition which is the convergence of a sequence. Next definition is convergence of a sequence. Convergence of a sequence. Now, a sequence xn, xn is said to be convergent, and the sequence suppose converges to x belongs to metric space x. Sequence is a function from set of natural numbers to in submetric space x. So, the sequence will converge in metric space. So, this x belongs to x if for given epsilon positive, for given any epsilon positive, there exists some natural number n, n belongs to set of natural numbers such that xn belongs to the open sphere centered at x, xn belongs to SR of x for all n greater equal capital N, for all n greater equal capital. This is the definition of convergence of a sequence in a metric space. A sequence xn is said to be convergent and converges to some limit x in metric space x if for every epsilon positive there exists some natural number such that the elements of sequence xn for all n greater equal n, the elements of xn belongs to open sphere SR of x. This xn belongs to SR of x for all n greater equal n means the, I will just do some rough work here. If suppose x1, x2, x3, x4, xk plus 1, then up to suppose this xn, then xn plus 1, xn plus 2, xn plus 3 and so on. These are suppose the elements of given sequence xn. Now, sorry, here n is infinite, set of natural number is infinite. X1 means when we apply x on 1 is the element of natural number, 1, 2, 3, 4 and so on are the elements of natural number. If we apply x on 1, then we get x1 and that x1 is in the metric space x. Similarly, if we apply x on the number of natural number, that is x on 2, then we get x2 in metric space xd. Similarly, for 3, if we apply x, then x3 is the element of this metric space x. Now, suppose x1, x2, x3 up to xn, xn plus 1, this set is infinite, this infinite set, that is this is the sequence, suppose this is sequence. Then we say that suppose this is metric space xd, set of natural number to metric space xd is a function. Suppose x1, this element is x1, suppose this is x2, this is x3, suppose this is x4, this is x5, this is suppose x6, x7, x8, 9, 10 and these are the suppose elements of sequence. Suppose this is x5, x6, x7, x8, x9, x10, but our sequence is said to be convergent. Suppose x5, x6, 7, 8, 9, 10, suppose x11 and so on. Now, we say that this sequence is convergent in metric space xd. Suppose this element is x, this element is x. Then we say that this sequence is converges to x whenever if we take any epsilon, and draw the open sphere, a sequence xn is said to be convergent and converges to x if for given epsilon positive there is a set of natural numbers such that xn belongs to xn belongs to S epsilon of x, not SR of x, S epsilon of x. For given any epsilon positive, if you take suppose this epsilon and draw the open sphere, suppose this is epsilon and draw the open sphere, then all the elements which are greater than n, so x n, now n greater equal n means this is suppose n, here suppose there is some natural number n and x n belongs to SR of x for all n greater equal n means suppose this there exists some n, suppose this is n, and after that n plus 1, n plus 2, n plus 3, n plus 4, n plus 5, all the elements lies inside this open sphere, the rest of the elements. So first n elements means xn, x1, x2, x3 up to x, these elements up to suppose this is xn, xn plus 1, xn plus 2 and so on, these all the elements of the sequence. If these elements up to this xn, all the elements up to xn are lies outside this open sphere, but the remaining element, that is xn plus 1, xn plus 2 and so on, all the remaining infinite elements are very close to x. That is, if you take any smallest epsilon, then for that epsilon there must be some integer n, for that after that n, the elements xn plus 1, xn plus 2 and all the remaining elements must be very close to x. Then we say that given sequence is convergent and converges to this limit x. Here I will draw the diagram. Suppose this is x1, x2, x3, this x, and suppose this is epsilon, then this open sphere must contain, suppose this is open sphere, then suppose this is sequence, and this sequence suppose x1, x2, x3, x, suppose this is xn, and the remaining elements, that is xn plus 1, xn plus 2, xn plus 3 are very close to this x. Then we can say that our sequence, suppose this is x1, x2, x3, x4, and then we say that this sequence xn converges to x. When we say that the given sequence is converges to x whenever for all n greater equal n, all the remaining xn belongs to that open sphere centered at x with epsilon radius epsilon. So this open sphere must contains the element of sequence for all n greater equal n. This is the definition of convergence. We say that given sequence is convergent if for every epsilon positive. If we take suppose this epsilon and draw the open sphere, suppose this open sphere, then there is some element n, this is n, and for this n all the remaining element, that is all the elements, suppose xn plus 1, xn plus 2, so this is xn plus 1, xn plus 2, which are must be close to this x. Then we say that given sequence is convergent and converges to this point x. This is just a rough work, there is no need to write this in your notebook. Up to definition of convergence, this is the definition of convergence. Now here this x is said to be limit point, sequence xn is said to be convergent and converges to x, then this x is said to be limit point of that sequence. This x is said to be limit point of that sequence, and we denote that limit n tends to infinity xn is equals to x, or limit of the sequence is x. So we will write here that small x is said to be limit point of xn, limit point of sequence xn. It is denoted by, that is sequence xn is convergent and converges to x, then it is denoted by xn converges to x, or limit n tends to infinity xn is equals to x, limit n tends to infinity xn is equals to x. This is the definition of convergence of a sequence in metric space. Now we will take one lemma. The statement of the lemma is limit of a sequence in metric space is unique. Limit of a sequence in metric space is unique. Limit of a sequence in metric space is unique. Now to prove this lemma, we will take here Statement of lemma is, if the sequence is convergent and limit of that sequence exists, then that limit must be unique. If limit of any sequence exists, then that limit is unique. Now here we have to prove that limit of any sequence is unique. We will take the sequence xn and in metric space xd, and we will take suppose two limits of that sequence, and if that two limits are equal, then we say that the given sequence has unique limit. So let xn be a sequence in metric space, be a sequence in metric space xd, metric space xd. Suppose the sequence xn converges to x, and that sequence xn again converges to y in x. Sequence xn converges to x, and that sequence xn also converges to y in x. Now we have to show that this x is equals to y. So our claim is x is equals to y. Now since this sequence xn is converges to x, so we can use the definition of convergence of sequence. Since xn converges to x, therefore for given any epsilon positive, there exists some, suppose n1 belongs to set of natural numbers such that distance of xn x, distance of xn comma x is less than that epsilon. So that xn belongs to s epsilon of x. This xn belongs to s epsilon of x means distance of this xn and x is less than given epsilon by definition of open sphere. So directly writing distance of xn with x is less than epsilon for all n1, for all n1 greater, sorry, for all n greater equal n1, for all n greater equal n1. Also given sequence xn converges to y, therefore for given again epsilon positive, there exists some natural number, suppose n2, such that distance between xn and y is less than epsilon for all n greater equal n2. Suppose this is equation number 1, this is equation number 2. We have to show that this x is equals to y. Whenever we can say that x is equals to y in metric space, if distance between x and y is equals to 0, then we can say that x is equals to y in metric space. Now if we choose the n, that is this n1 and n2, if we choose the maximum between n1 and n2, then clearly our condition of this distance of x and x is less than epsilon and distance of x and y is less than epsilon is satisfied, because this, suppose we will draw the another diagram. Suppose this is the metric space xd and distance between x and x, suppose this is x and this is suppose open sphere centered at x with radius epsilon, with radius suppose this is epsilon. Then again distance between x and y is less than epsilon. So suppose this is n1 for first case and suppose this is n2 for the second case. Suppose this is n2, then distance between xn and x is less than epsilon, distance between x and y is again less than epsilon, and if we choose here n1 and n2, if we choose this maximum between these two, so clearly xn, this xn is less than epsilon for if y is center, and this xn and x is less than epsilon if x is center. So there may be possibility for the bigger open sphere that the some elements here may be here. So if we choose the maximum between these n1 and n2, suppose this is n1 is maximum, then the condition is satisfied for both the cases, for all the xn which are very close to x, or here we know that x and y are equal because limit is same. So for these elements, so suppose this was our first open sphere, this was our second open sphere, and this is suppose n2, this is n1. If we choose the maximum number between n1 and n2, so here n2 is maximum, sequence is coming from here, the elements of the sequence are here, this is maximum, then obviously both the condition, distance between xn and x less than epsilon, distance between xn and y is less than epsilon, both the conditions satisfied for these elements. So there is no need to write this diagram. If we choose n is equals to maximum of n1 and n2, n is equals to maximum of n1 and n2, therefore we can write this distance of xn comma x is less than epsilon and distance of xn comma y is less than epsilon for all n greater equal n. These both inequalities satisfied if we choose the maximum between n1 and n2, distance between x and x, distance between x and y, both are less than epsilon for all n greater equal n. Now by using this, all the things are happening in metric space, so we can use the properties of metric space. So by triangle inequality, therefore by triangle inequality we can write distance between x and y is less than or equals to distance between xn comma x plus distance between distance between x comma xn, or write it as x comma xn, and distance between xn comma y, distance between x and xn plus distance between xn and y. This is the triangle inequality. Now clearly distance between x and xn is less than epsilon, again distance between x and y is less than epsilon. So this epsilon plus epsilon will become 2 epsilon. Distance between xn and y is less than 2 epsilon, but epsilon is very small, so epsilon tends to 0. So distance between x and y tends to 0, that is x and y are equal. Instead of taking epsilon on both the cases, if we take this for all epsilon by 2 positive, again if for all epsilon by 2 positive, this is less than epsilon by 2, again this less than epsilon by 2, then we can write this is again less than epsilon by 2, epsilon by 2. This is just for our simplification, that is epsilon by 2 plus epsilon by 2 is epsilon. So we can write it as this distance between x and y is strictly less than epsilon. So this epsilon by 2 is just for our simplification. If we take epsilon, then again proof is obvious, because epsilon plus epsilon is 2 epsilon, and as epsilon is very small, so that epsilon always tends to 0. Epsilon is very small number, that is distance of x y is tends to 0. So this x and y are equal. So for that, instead of writing 2 epsilon here, I will just write epsilon, and for that this is just a simplification, that is construction epsilon by 2. Epsilon by 2, because the definition is for all epsilon positive. So clear, for epsilon by 2 is a positive number. So epsilon by 2 positive, there exists n1. Similarly for epsilon by 2 positive, there exists another natural number n2, and if we choose the maximum between these two, then both the inequalities are satisfied. So distance between x and x is less than epsilon by 2, again distance between x and y is less than epsilon by 2. So using these two equations 1 and 2, we can write distance between x and less than epsilon by 2, distance between x and y is less than epsilon by 2, which is, so this implies distance between x and y is strictly less than epsilon. This implies distance between x and y is less than epsilon, but epsilon is a very small, but epsilon is very small, and that epsilon always tends to 0 implies distance between x and y is less than epsilon. Distance x y is less than epsilon, and epsilon is very close to 0. So number which is this epsilon is a number which is very close to 0, and this distance of x y is less than that number. So clearly distance between x and y is equals to 0. So this implies x is equals to y. Hence the limit of a sequence in the metric space is unique. Hence the limit of a sequence in metric space is unique. Now the next example is show that xn, that is sequence xn in metric space xd converges to some x if and only if if and only if distance between xn and that x is converges to 0, that is converges to 0 means tends to 0. So that xn in the metric space xd, a sequence in metric space xd is converges to that x in that metric space if and only if distance between xn and x converges to 0, that is distance between x and xn are nearly equals to 0. So, to solve this example, suppose first of all we will suppose xn is converges to x, then suppose the sequence xn converges to x. So, sequence converges to x, by definition we can write if and only if for epsilon positive there exists some natural number n such that distance between x and xn, that is xn belongs to yes epsilon of x means distance between x and xn is less than epsilon for all n greater equal n. This is definition. So, we can write if and only if. Now, this is possible if and only if mod of, we can write this distance of x xn less than 0. So, we can write mod of distance between x xn minus 0. We can write this distance of x xn minus 0 is less than epsilon for all n greater equal n, for all n greater equal n. So, this implies by if and only if distance of x xn tends to 0. By definition, again by definition we can say that epsilon delta definition, distance between x and xn minus 0 is less than epsilon, means distance between x xn tends to 0. Mod of distance of x xn is less than epsilon, epsilon is a very small number. So, we can write distance between x and xn tends to 0. So, our sequence in metric space converges to x whenever distance between x and xn tends to 0, hence the solution.